GameSci.com. GameSci.com.
Heidi-ho, neighbors! Time to talk about random access files, input-output. RAM memory is transient, it disappears without power. Disk memory is persistent, it sticks around after shutdown. Let's talk about sequential access. Sequential access files means data is read line by line. To get to the end, you must read every line. Random access files means data can be read from any point in the file, jumping to the beginning, middle, or end to read or write data to the file. In a sequential access file, you'll start at the beginning and you'll read every line of data as it goes. And to read to the end, you have to read the lines before it. Random access files let you jump around. You can jump from the beginning to the middle, back to the beginning, to the end, read a little at the end, jump backwards. You can go anywhere you want in a random access file and read and write data from that location without reading the data in front of it. Sequential access means the file is opened and the first line of data is read. Each subsequent read advances the file pointer to the next line of data. If you read this first line, it will bump you down to the second line automatically after reading the first. Now, sequential access is not bad. Sometimes you want to read every line in the file. For example, if you have a large amount of data in a text file that needs to be imported into a database, open the file, read it line by line, and insert that information into the database. This is the information that is stored on disk, and I'm going to read it sequentially by going through every line of the file. In Java, using the scanner class to read a text file can be sequential. Using the printWriter object to write a data file can be sequential. Every computer language that supports file I/O supports sequential access to a file. I'm just reading this data line by line, and eventually I'll reach the end and read the last line of data. Below is a code snippet of reading a text file sequentially. I'll set up the name of the file, I'll build my file object, I'll create a scanner on that file object. And while input has next line is true, I'll read the next line of data from the file. Spin in this loop and read line by line until I've read through the entire data file. And of course, when has next line goes to false, the loop will exit and I'll do my input.close. This will read each line and stop after the last line of data. This little piece of code is an example of sequential file access. Start at the beginning and read all the data till you get to the end. Random access means the file is opened and any part of the file can be read or written. The beginning, middle, or end of the file. Each subsequent read or write can be from anywhere in the file. I'm going to say go read sector 4 and I can jump straight to sector 4, read sector 4 and send it back to the buffer. I did not have to read sector 0 or sector 1 or 2, just jump to sector 4 and read it, transfer the bytes to the buffer array. That's what random access means. Now my picture of the file here is a little bit different. Sector 0, this is a file on disk. Sector 0, Sector 1, Sector 2, Sector 3, Sector 4. See that dot, dot, dot? This file can go on, dot, 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 pick it up, Sector N-2, Sector N-1, Sector N. This is the last sector of the file. This is the first sector of file. This could have hundreds, if not thousands, of sectors in between. Random access means any sector of the file can be written. Most algorithms that update disk sectors read a sector in RAM buffer, change the data in the RAM buffer, and then write the RAM buffer back out to the sector. I'm going to execute some code here. Write sector N using this buffer, and it will jump to the end of the file and write data at the end of the file. Again, I didn't have to write sector 0 or 2 or 4. All I did is jump straight to sector N and write it. I transferred the data in the RAM buffer here to the disk drive. This example is purposely jumping around to different sectors because that's what random access means. When a file is first opened, it starts at the beginning. Most languages use some sort of a seek function to move within a file to go read or write a particular sector. So I'm going to read sector 0. It's going to seek to the beginning of the file, read that sector, and load it into this buffer. That's what a random access file does. The seek varies by language. Usually you can move to an absolute or relative position. But the seek command is extremely important for random access files. It says move to a particular position in the file, be that sector 0 or sector 4 or sector N. A clear application of the random access file is the hash table bucket approach. During a find, the hash function returns the bucket or sector number of the key, and a random access jumps straight to that bucket. I'm going to call hash me and pass it a key. It's going to return a bucket or sector number where that key should be located at. Read sector will then seek or random access to that bucket number, read it into RAM memory, and store it in my buffer. Once the data is in RAM, the buffer can be searched for the given key. If you cannot jump to a particular sector, you're going to have a hard time doing the hash table bucket approach. That is the key, jumping or seeking to a position in the file and reading the data that hopefully contains your data. When an update needs to be made to a hash bucket, a read into RAM memory buffer is done. The changes are then made to the data in the RAM buffer, and the buffer is then written back out to the disk drive. Again, this is a code snippet, not a full example, but it is a good picture of what a write to a hash bucket has to be. I'm going to hash the key that I want to insert into the bucket, and it's going to tell me which sector or bucket number to store it. Let's say this returns sector 1 and says I want to store this in bucket or sector 1. I'll read that sector into RAM memory and then change or insert or delete the record that I want to operate on while it is in my RAM memory buffer. Once the changes are complete in the buffer, I will then write sector that same bucket number out using that same buffer, and I'll update the data on the disk drive in the proper sector. Remember, hash tables are order of one algorithms. This function, this piece of code snippet, requires one sector read and one sector write to insert or change something in a hash table. Some notes. We still need the open, read write, and close pattern to use random access files. Read sector and write sector are user-defined functions that must use the seek function to position to a file. Random access files are the core of any database written in a high-level language like Java or C++. Some databases written in low-level languages even access the hard disk BIOS directly to access the sector read and write functions of the drive. This is a generic description. The code snippets are not meant to be copied and pasted. Specific examples will follow. Random access write file. Here is a small example program that will create/write a random access file to disk. First, we import the Java I/O package. A package is a group of classes. The star wildcard matches many. This code adds the following classes to the program: random access file and exception. And it would pull in any other classes we need from the I/O package if we started using them. This is a typical first line of the program. By now we've written plenty of Java programs. I shouldn't have to explain this line. There's something new here. Public static void main string array args throws exception. That's the new part. Many things can go wrong when accessing a file. File not found, no such directory, no write permission. Adding throws to the method header is the easy way to process errors in file I/O. It's not the best way. It prints an error message and terminates your program, but it is easy. Using try catch is always a better solution. But for now, let's take the easy solution and add throws exception to any method that does file I/O. String file name equals data.db. Using a variable to specify the file to open is much better than hard coding. In this case, the file will default to the working directory, which is your project folder in many IDEs. The .db is not required, but it informs anyone looking at the file name it is a database file. This example does not go so far as to create a real database. Hash buckets would be an example of a real database file. Int age equals 19. A simple variable to demonstrate how data from a non-text item is output to a file. The code below shows hard-coded data and data from a variable written to a file. Note, using variables is almost always a better way to do it, also demonstrating conversion between numeric, string, and byte types. Not shown is a string.valueOf, which also converts between types. Random access file, RA file. It is very important. The class name random access file pretty much explains what it is, what it does. Java, as an object-oriented programming language, uses objects to do most, if not all, file operations. Get used to it. This is a declaration only, so a reference variable with the initial value of null is created. The object is created on the next line of code. All access to the file will occur through this reference. Here's the reference I just declared RA file. Since I haven't assigned an object to it yet, it contains the value null. RA file equals new random access file, passing it a file name and a parameter RW. This line of code will open and create a file for read and write access. A random access file object is one of several ways to write or output data to a file. Note the RW parameter. This is read-write mode. Using just R is read-only mode. This call is not destructive. If data.db contains existing information, it will not be overwritten. Only the data sectors that we write to will be overwritten. Here is the random access file object that was created and assigned to RA file. If you want to get access to data.db, you need to go through this object to do it. Byte array buffer equals new string, and I'll pass it John Doe is plus age.getBytes. Buffer is my sorry excuse for a record. Not enough space to do a nicely formatted 128 character record. It does show data conversion. Age is converted to text and getByte converts the string to an array of bytes. Recall the layered approach. This shows data in RAM memory converting to a string converted to bytes suitable for writing to disk. So I'm building a string John Doe is 19. Once I've built that string object, I will convert it to an array of bytes, and that array of bytes will be assigned to the variable buffer. System.out println new string buffer. And I'm going to output whatever's in the buffer to the console, and you can see John Doe is 19 showed up. By now, students have used system.out many times to display to the console. This example is to demonstrate how easy it is to convert back and forth between string and byte array. For students just learning databases, read-write of pure text records makes it easy to view the records on the console or with a text editor by opening the file. GetBytes converts from a string to an array of bytes. This string constructor converts from an array of bytes to a string. We like to write bytes to a file. We like to write strings to the console. rafile.seek 4096. We're going to issue a command to our random access file object. This is the random access. The seek method says move the file pointer to byte 4096 of the file. Any read-write will occur at that position in the file. Note the ... shown on the disk. This is blank space that will be allocated in the file, null filled. The seek method can move to any file position it wants. What if we had a sector size of 512? 4096 divided by 512 equals 8. This seek would be taking us directly to sector 8. rafile.write of the buffer. Issue a command to the object to write data to the disk. Write the buffer to the file. Go to the rafile object and run the write method. That's the left arrow you're seeing here. Then have the write method send the data to the file. That's the right arrow that you see right here. Notice how it moved past the blank space, the dots, and wrote starting at byte 4096. Random access means seek can move to any position, and the next write will happen at that position. This line of code has got to be looked at before you understand this line of code. Jump to position 4096 in the file and write data starting at that position. These dots here are the blank space between the start of the file and 4096. RAFile.close. Close the connection to the file data.db. This is important for two reasons. It releases the lock on the file that prevents others from accessing or changing the file, and it flushes any pending writes to the disk. Never consider a write to disk complete until the close is done. Small data writes are buffered until a flush is done, and the close guarantees that this data is flushed to the disk drive. The closed curly braces mark the end of main and the class. The variables created in RAM, as they should, disappear. My random access file, RA file, went away. My file name, my age variable, all of that stuff disappears. Stopping the program, let alone powering off the computer, is enough to delete any data stored in RAM. But what sticks around? The data written to the disk does. A day, a week, or a year later, it can still be there ready to be loaded back into RAM. Before we leave this slide, let's look at some options. Notice what I did or changed in the red box. This is called an absolute file name, and it kind of sucks. It is very Windows specific, won't work on other systems, or on another machine without the C:\J folder. But sometimes students tell me they do not know where their project folder is. That's sad, but this leaves no doubt where the file will be. Do not recommend coding like this. Try to avoid using absolute file names. Here's another option. I've changed the code inside the red box to use a relative path name. This is called a relative file name or a relative path, and it is much better. It says the file will be in a subfolder docs of the current working directory. Works on any system. Very useful if you're creating hundreds of files. Just be sure there is a docs folder in your working directory, or it's a file not found error. Sometimes the error messages can get a little weird. It'll say file not found, but the problem is with the directory name, not the file name. Made another change. Probably not a good change. What I'm doing is I'm hard coding the name of the file when I open it. You can hard code the file name, but it is not a good idea. If your program has 15 different places where it opens a file, that is 15 edits if the file name changes. Better to use a variable than it's one edit at the top of the code. I know I lecture a lot about not using hard-coded values, then use them in my example. John Doe is hard-coded. RW is hard-coded. This 19 is hard-coded. But I need to keep my coding samples short and simple to fit on a slide. So do as I say, not as I do. Try to avoid hard coding things like file names and data you're writing to the file. Check out the red box. I made another change. Here is a way to code it so you don't have to change the code even when the file name changes. The args parameter to main is for the command line arguments that you can pass when it runs. If I were to execute this code from the command line, java random access file write data.db, data.db will be passed to the arg0 array, and you can open that file. Now the user of the program names the file and can change it all at once. The program does not need to be changed. Keep in mind, we have written a file to disk. On the next slide, we'll learn how to read that data and assume it's not been changed. Text files are nice because they're easy to change. A program like Notepad or an IDE editor can open and edit a text file. Users can also delete files from the system. But for the next slide, assume it has not changed. So here's our file on the hard drive, data.db. It's got a bunch of blank space, and then at position 4096, John Doe is 19. Random access read file. A small example program that will read a random access file from the disk. Note the data that was written to the file in the previous example is still sitting on the hard drive below. Port to Java I/O package. A package is a group of classes. The star wildcard matches many. This code adds the following classes to the program: random access file and exception. This is a typical first line of a file. We should all recognize this by now. Here's the new thing, the throws exception on main. Many things can go wrong when accessing a file. File not found, no such directory, no write permission. Adding throws to the method header is an easy way to process errors in file I/O. It is not the best way. It prints an error message and terminates your program, but it is easy. Try catch is better. Keep in mind, this file is sitting out on the disk. If someone deleted it, then when you go to read it, it's going to be an error. So you always have to be prepared to handle errors when doing file I/O. String file name equals data.db. We're using a variable to specify the file to open. It is much better than hard coding the file name. In this case, the file will default to the working directory, which is usually your project folder in many IDEs. The .db is not required, but informs anyone looking at the file name it is a database file. This example doesn't read a real database, it just reads the example that we wrote in a previous slide. Int age, a simple variable to demonstrate how data read from a text file can be converted back to numeric, also demonstrating conversion between numeric, string, and byte types. Not shown is a string.value of, which also converts between types. Whenever you have an integer in computer memory, string.value of can convert it to a string. Random access file, RA file. This is important. A class name random access file pretty much explains what it is, what it does. Java as an OOP language uses objects to do most, if not all, file operations. Get used to it. This is a declaration only, so a reference variable with an initial value of null is created. The object is actually created on the next line. All access to the file will occur through this reference. Here's the reference right here. Since I didn't exactly assign it an object up here, it contains the value null. This line will open a file for read-only access. RA file equals new random access file. File name, R is the second parameter. The R means read only. A random access file object is one of several ways to read or input data from a file. Note, use the RW parameter for read-write mode when you plan to also write data to the file. This call is the open part of the pattern. Open the file, read and write your data, close the file. At the open, the file pointer will be at position 0 of the file. By default, you always start at the beginning of the file. Byte array buffer equals new byte 14. Buffer is my sorry excuse for a record. Not enough space to do a nicely formatted 128 character record. John Doe is 19 is exactly 14 characters. The size of the buffer array determines how many bytes it will try to read. Make it the size of a sector to read an entire sector, or the size of a record to read a single record. Buffer is in RAM memory. We need to transfer the data from the disk drive to RAM. RAFile.seek 4096 instruct the random access file object to seek to the middle of the file. Seek to this position in the file. This is the random access. The seek method says move the file pointer to byte 4096 of the file. The next read will occur at that position in the file. Note the ... dots shown on the disk. Skip the blank space that was allocated in the file that's null filled. The seek method can move to any file positions it wants. If we had a sector size of 512, 4096 divided by 512 equals 8. This would be sector 8. RAFile.read of buffer. Read the file to the buffer. Go to the RA file object and run the read method. That's this left arrow here. Then have the read method send the data to the buffer or RAM. That's this right arrow here. The request is made. Send the data that you can find back to the buffer. This is passed by reference. Any data written to the buffer will exist in the buffer. Notice how it moved past the blank space, the dots, and read starting at byte 4096. Random access means seek can move to any position and the next read will happen at that position. By now, students have used system.out many times to display to the console. All I'm going to do is take my buffer, convert it to a new string, and output the string to the console. This example shows the data read from the file and demonstrates how easy it is to convert from a byte array to a string. For students just learning databases, read and write of pure text records makes it easy to view the records on the console or with a text editor by opening the file. rafile.close. Close the connection to the file data.db. This is important for two reasons. First, it releases the lock on the file, especially when you're using read-write. That prevents others from accessing or changing the file, and it frees the OS resources used to open the file. Never leave a file open longer than it's needed, especially when you're open for write access. Basically, it puts a lock on the file while you're writing to it. The close curly brace mark the end of main and the class. The variables created in RAM, as they should, disappear. File name is gone, age is gone, RA file is gone. Stopping the program, let alone powering off the computer, is enough to delete any data stored in RAM memory. But what sticks around? The data written to the disk does. A day, a week, or a year later, it could still be there, ready to be loaded back into RAM. Let's make a slight change to the program. Focus on the red box. Before we leave this slide, let's look at some options. Let's open the file for read-write access. Then read the same data from the file into RAM buffer. This time we're going to modify the data while it is in RAM and then write the data back to a file. I'm going to read the data into the buffer. After I've read it into the buffer, I'm going to parse int using the string buffer a substring starting at position 12 and add 1 to that value. Wow, what is this complicated line of code doing? What it's doing is it's extracting the two characters at the end of the buffer using substring. It converts the letters 19 to the number 19 using parse int, adds 1 to the 19 and stores the result 20 back into the variable age. Arithmetic can only occur on numeric variables in RAM memory. Now let's update the buffer with the new value of the age variable. I have my buffer. It contains data. What I want to do is execute this line of code now. Buffer equals new string, and I'm going to reset the data with the new age variable. Update the buffer with the new value of the age variable. The pattern to update a database is this. Read the sector or record into RAM, update the data while it's in RAM, and then write the sector or record back to disk. I'm not crazy about this code. It's not great, but it had to fit on one slide. I had to read in the data, add 1 to the age variable, and reset the buffer. Once my buffer is reset, I'll seek back to the same position I was at before and write the buffer back out before I close the file. Seek back to the original position in the file, write the updated buffer back to the file, and close the file to flush right to disk and free the OS resources. Notice how the data on the hard drive updated to 20. Every time a student has a birthday, I read in their data, change their age value, and write it back out to disk. Again, I'm not crazy about this code, but if you look below, the new age is written to the disk drive. This is sort of a forced example. I had to keep it short so it fit on a slide. I want you to understand I'm reading the data off the drive, changing it while it's in RAM memory, and then flushing it back out to disk down here. For a true hash table bucket database file, the pattern to update the disk would be this. read the hash bucket into RAM. Update the data in RAM, write the hash bucket to disk. Each time this program is run, it will bump John Doe's age by 1. If I ran it again, it would extract 20, add 1, make it 21, convert the whole thing to a string, and write the whole string out. John Doe is 21. Database functions read. I like to isolate my database read and writes to a small section of code. Here's an example that uses a random access file to read an entire sector of data from the disk and return it to a caller. Set up a private int sector size of 512. This is the size of the disk sector. A global variable set to a hard drive sector size. Common sizes are 512, 2048, 4096. Make this easy to change or configure so the same code can be used with various hardware. Keep in mind this is a code snippet, not all the code shown. Code to open and close the random access file RA file is needed for this code to work properly. Public byte array read sector int sector number. This is a function to read an entire disk sector from the hard drive. The input is a sector number 0, 1, 2, ... all the way to the end. The output is an array of bytes from the disk. When I call read sector, it will output the data that's in the sector to this byte array. If I said read sector 8, assign the bytes in sector 8 to the variable data. Byte array buffer equals new byte of sector size. Set up an array of bytes to buffer the data in RAM, read from the hard drive. Here's my buffer. This is just an array of 512 bytes. The try command. Try this code, see if it works. File IO code sometimes does not work. If anything goes wrong in the try block, jump and execute the code in the catch block. This try catch allows us to get rid of throws exception off of this method header. RAFile.seek to sector number times sector size. Seek to the position in the file where the sector is located. The math is fairly easy. Sector 0 times 512 is 0. Sector 0 starts at position 0 of the file. Sector 1 times 512 equals 512. That's where sector 1 of the file is. Sector 2 times 512 equals 1024. Sector 2 starts at byte offset 1024. We're doing an 8 times 512 because we're trying to read sector 8. That means we want to advance to position 4096 in the file. Int numbytes equals RAFile.read of the buffer. Read the data from the drive and using pass by reference load it into the buffer. The function returns the actual byte read. It should be 512 for a full sector. -1 indicates no bytes were read. This is where the data is transferred from disk to RAM. Read the data from the file into the buffer. If this should return a negative number, that would not be good. If numbytes equals -1, let's return null. This is error checking. It should be 512 for a full sector, less than 512 for a partial sector, and -1 to indicate no bytes were read. Most likely trying to read a sector past the end of the file or trying to read a file that doesn't have any data in it. In that case, read sector will simply return null to indicate there is no data read from the disk drive. When the condition is false, the try block finishes and the catch is skipped. A reference to the data read from the disk is returned to the caller. Note the buffer is declared as a byte array, and that is exactly what the return type is for this method. As a false statement, I'll jump to the end of the code. The buffer will contain the info that I read off the disk and return it to the user. Then it'll fall through to this curly brace and finish. When the function completes, the local reference variable buffer is deleted. But if this was the call that was made, the data reference variable is assigned to the byte array and the caller can access the sector using this reference. Only when the data reference is gone will garbage collection delete the byte array. Important. Let's connect this line of code to there. Here's the catch command. The catch will only execute when seek or read fails and throws an exception. Only the code in the try block can force it to the catch. Any code after the exception in the try block will be skipped and it will go directly to the catch. The reference E will contain information on what caused the exception and can be used to find out what the problem is. If the catch was called, this is what would happen. System out print line error sector, and I'd print out the sector number, and then I'd print out E, which would be a reference to the object which explained what went wrong. We're going to print a message so the user can understand what caused the exception. Showing the sector number is kind of a no-brainer. It will allow the user to know where in the file the problem occurred. The reference E is also printed. The system does the best it can to describe the cause of the exception. Sometimes you want to print out the error message yourself. This is a hard exit from the program. System.exit -1. I went to read the file, it wasn't there. This code decided to leave, to exit, and not run anymore. The code does not have to do this, but when a read fails in the middle of the read of a file, it's usually serious. The simple errors like file not found happen on the open. The other simple error, reading a sector that does not exist, does not throw an exception. If num bytes equals -1, that will handle the problem and tell the user that it couldn't read any data from the file. Keep your database file access isolated. Place the code in a library or package and have all your programs use the same code to open, read, write, and close the data. Think of it like an ADT or an abstract data type. Database functions write. A short method to write a sector to the disk drive. I like to isolate my database read and writes into a small section of code. Here's an example that uses a random access file to write an entire sector of data to the disk. We'll start with a global variable set to the hard drive sector size. Common sizes are 512, 2048, 4096. Make this easy to change or configure so the same code can be used with various hardware. This is a code snippet. Not all the code is shown. Code to open and close random access file RA file is needed for this code to work. Public void write sector. Pass it a sector number and a buffer that you want to write. This is a function to write an entire disk sector to the hard drive. The input is a sector number 0, 1, 2, ... all the way to the end. And it is also the buffer of the data that you wish to write to the hard drive. The output is none. Huh? Wait a minute. The output is the data on the disk drive. It is going to write a sector to the disk drive. Technically, the output isn't returned to the caller. Technically, the output is sent to the disk drive. What if we were to call write sector, pass it an 8, and the buffer we wanted to send data to the drive? Write the data in the buffer parameter to sector 8 on the hard disk drive. The size of the buffer should be sector size. Once again, we're using a try catch statement. Try literally means see if this code works. File IO code sometimes does not work. If anything should go wrong in the try block, jump and execute the code in the catch block. RA file.seek to sector number times sector size. Seek to the position in the file where the sector is to be written. The math is pretty easy. Sector 0 has a byte size of 512. Its offset is 0. Sector 1 has a byte offset of 512. Its offset is 512. Sector 2, byte offset of 512. It's located at 1024. What if I wanted to go to sector 8? I'd do 8 times 512, and that would be position 4096 in the file. Notice the arrow. I'm telling the file to move its write position to the middle of the file. RA file.write of the buffer. Write the data to the drive. This is where the data is transferred from RAM, where it was in the buffer, to the disk drive. Write sector 8. Here's the data buffer. Send it out to the hard drive. Maybe a check should be added to make sure buffer.length equals sector size. And pad the buffer with nulls or spaces it does not need. This is the end of the try block. When it hits the end of the try block, if nothing bad happened, it'll jump past the catch. When the try block finishes without a problem, the catch is skipped. Note the generic something new was written to the disk by the previous line because the code has no idea what the caller passed to the buffer parameter. I just plugged in something new. If the write went just fine, it will skip the catch and hit the curly brace down here. When the function completes, the code returns to the caller. The method has a void return type, so no need to return anything. I like to create a small set of functions, one to open the disk, read the sector, write the sector, and close the disk, and have all the database I/O go or occur through these functions. Easier to change if you isolate your database code into a small set of routines. Important, catch will only execute when the seek or read fails. Throws an exception. Any code after the exception in a try block will be skipped. So if this line of code fails, it'll jump to the catch and skip the write. The reference E will contain information on what caused the exception and can be used to find out what the problem is. Here's just an example of the catch executing. We're going to system.out println to the screen what sector number had a problem, and hopefully we'll get a nice description in the E variable. Print a message so the user can understand what caused the exception. Showing the sector number is kind of a no-brainer. It will allow the user to know where in the file the problem occurred. The reference E is also printed. The system does the best it can to describe the cause of the exception. If you just print out E, you should get at least a reasonable message on what happened to your program. This is a hard exit from the program. System.exit with a -1 says terminate my program. The code does not have to do this, but when a write fails in the middle of the file, it is usually serious. The simpler errors like file not found happen in the open. Done. Keep your database file access isolated. Place this code in a library or package and have all your programs use the same code to open, read, and close the database files. Think of it like an ADT or an abstract data pipe. I want to isolate my data code into one .java file, one big nice class. Then I can use it in multiple programs if I start up a new program.
GameSide.com.